Hello, my name is Joshua Taylor, and this is my video lab report for Lab 2, Lines of Charge. Here's a table of contents. The purpose of this lab is to computationally model two line-charged tapes exerting electric force on each other and estimate each tape's charge so that one floats above the other. Models used to do so are solely computational, with a system of charged tapes. The lab successfully determines the excess charge on one piece of tape to be positive 2.135 e negative 8 coulombs. Here are some relevant equations and principles. We're going to need the electric force equation, which is 1 over 4 pi epsilon naught times Q1, Q2 over the magnitude of R squared times R hat. The electric field equation is the same as the electric force equation minus the charge that is being acted upon. 1 over 4 pi epsilon naught is a constant known as 9 times 10 to the ninth. And like charges repel while opposites attract. Some other things we're going to need are the fact that the force of gravity near the Earth's surface is equal to negative mass times gravitational constant in the y direction. Newton's second law states that force is equal to mass times acceleration, and Newton's third law states that every action has an equal, opposite, and collinear reaction. The only model we'll be using is a computational model of the two-line tape system and the acting forces. A recap of the experiment from last week that this is based off of, we took pieces of tape and created two pieces of charged tape by ripping one piece of tape, a U-tape, off of a base tape. We suspend one piece of tape, tape B, in the air and place the other charged piece of tape, tape A, below it so that the two like charged pieces of tape repel each other, and ultimately the electric force of the bottom overcomes and equalizes the force of gravity acting on tape B. We record the distance between the two tapes when equilibrium is reached. So some data and assumptions. The tape length is effectively 0.1 meters. That was covered last week. Same as tape mass. The tapes have positive charge. Each piece of tape is assumed to have an equal and equally distributed charge across its length. Each piece of tape is assumed to be a one-dimensional line. We ignore air resistance. And last week, we experimentally calculated the charge on a piece of tape to be 1.212 e negative 8 coulombs. Now, for this week, we're going to use code, and we're going to set some initial values. G is 9.81. That's the K constant we talked about earlier. We set the initial mass of one piece of tape. This was experimentally found through trial and error after we got the rest of the code figured out. Length of a piece of tape, distance, these are initial conditions. Function for the electric field was used in lab 0. We brought that over. And then code creating lines of charged tapes. And this is all the code to create this model. In blue, we have tape A below tape B in red, and we see in green all of the individual forces, electric forces exerted by tape A on tape B. In white, we see the net electric force, and in yellow, we see the net gravitational force. These two cancel each other out, and that occurs when the charge of one piece of tape is 1.7604 times the originally thought charge on one piece of tape. So there is a difference in calculated charge depending on how you model the tape. We'll explore this further in the preceding slides. Possible sources of error include the assumptions made of equally charged lines and of tape distributed evenly, possible coding errors, and the neglection of air resistance. Now, what if you had modeled each tape as a single point charge like in the previous lab? Well, like in the previous lab, the calculated tape charge would be 1.212 e negative 8 coulomb. While using this line charge model, the charge is calculated to be 2.135 e negative 8 coulomb. And why do these estimates differ? Which one's closer to the real value? Well, assuming that the tapes are point charges causes all the electric force to be along the same line of action and fully contribute to the neutralization of gravity. When the charge is distributed along two lines, the electric forces act in many different directions, and the forces in the x direction are assumed to cancel out. Therefore, a greater magnitude of charge must be present so that the same force in the y direction can be generated as some of this x force is lost. The line of charge more accurately models the real-life system and interactions, so it is probably closer to the real value. So, in conclusion, tape charge estimates differ based on the models used and assumptions used. A line charge model of charged tapes is more accurate, and the tape's newly calculated charge is 2.135 e-8 coulomb. Thank you.